The ball is caught in a glove by a glove, and the ball decelerates from an initial speed to rest at a rate of 2.1 times 10 to the fourth meters per second squared. Okay, so they give us an acceleration over a period of 1.85 milliseconds. Milli is 1 times 10 to the negative third seconds. Determine the initial speed of the ball. Okay, so this is going to be a kinematic equation. So first thing you do with pretty much all kinematic equations is you write up the kinematic equations. So I like to start with acceleration equals acceleration. Velocity equals at plus v naught. And x equals 1/2 at squared plus v naught t plus x naught. The reason I like to start with a equals a is what you're saying is a equals some sort of constant acceleration. I know I could write like a little zero there. I don't. Then you take the integral of it with respect to time, you get something like this. Take the integral of velocity and you get position, which is going to be something like this. And this assumes a constant acceleration. Do they say constant? Bump, 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 bump. They don't say a constant acceleration, but we're going to assume it just because the problem becomes impossible otherwise. Okay, so focus, focus. So we have a light blue. Now I'll do green. We have an initial speed, comes to rest, which gives us a final speed of 0. We have an acceleration, and we're given a time. So we're actually trying to find the initial speed. So we don't have that yet. But we have, so basically long story short, we will use the middle formula. So rearranging this, we have v naught equals at minus v, which we know that the final v, this is v final, will be 0. So we do acceleration times time, which is going to be 2.1 times 10 to the fourth. And I'm going to put in the meters per second squared here. I don't always do that, but I'm going to do it this time just as kind of a backup check to make sure that the dimensions work out correctly. 1.85 times 10 to the negative third seconds. And I just converted milliseconds into seconds. Whoop. Yep. And so one of the seconds will cancel. And we're left with equals, zoom in. All right, focus on the handwriting being a little bit better. 2.1 times 1.85 times 10 to the fourth times 10 to the negative third. When these powers combine, they get 10 to the first, which is just 10. So I'll do 21 times 1.85, which will be about, let's say 37. 37. And that will be in meters per second. See what the possible answers are? I suspect it's going to be that one right there. So let's see, 21 times 1.85. Whoop, go to the wolfram. 21 times 1.85. And we get, 38.85. Go back, 38.85. That'll be our answer. So that is how this problem is done. So what do you think about this? Going back, kind of recapping, if you will. A ball is caught by a glove, decelerates from an initial speed to rest. So from an initial speed, so mystery initial speed to rest, which we know is a final speed of 0. And we're given some numbers, an acceleration, and a time. So we're kind of thinking here, all right, kinematic equations. Write down our 3 kinematic equations. There's kind of a fourth one. We'll deal with that one in future problems when it comes up. Basically what you do is you solve for t and then plug it into the other one, and it's kind of useful sometimes. Find out which kinematic equation to use, plug in some numbers, check our dimensional analysis, make sure that the units match up correctly. Because if they don't, then we know that something's probably wrong. We should fix it. We estimated an answer. You don't have to estimate an answer. You can just plug it straight into your calculator. Not a big deal. Took our answer and found it on the left side. So that is how this problem is done. Hope that helps. I will see you on the next problem.